Hi guys, I hope you're doing good. In this video, I'm going to show you how to prove the completeness theorem for proof trees. Hello everyone, welcome to the Attic. My name's Mark Jago. I'm a philosophy professor in the UK. In this video, I'm going to walk you through the completeness theorem and how we prove the completeness theorem for the tree test, for proof trees. So in recent videos on the channel, I've been building up to this result by going through what soundness and completeness mean and how we can manipulate the statement of them to kind of make these proofs a little bit easier. So I suggest you have a look at those first before we dive into this proof itself. Okay, so if that sounds good to you, do me a favour before we get going, give this video a thumbs up, that really helps me out, and if you're enjoying this kind of stuff, it would be great to see you subscribe to the channel. So before we get going, I want to just give you a heads up. When we looked at soundness, what we did is kind of atomistic. We had to go through each rule one at a time and show that each is sound, okay? But each little one was quite simple. For completeness, it's not like that. It's much more holistic. We have to prove that the system as a whole is complete. We can't show it for each rule. It wouldn't make sense to talk about individual rules being complete. We have to show it for the whole system. So the completeness proof, we have to do all of it, and that is going to make it a little bit more involved than the soundness proof. Okay, so we're going to try and work through it slowly and carefully. And look, if it all starts to feel a little bit too big, a little bit too much, a little bit too complicated, just take a step back. Go and watch the early videos again, go and watch the early part of this video again, and I promise you, if you put enough patience into it, it's gonna make sense eventually. Okay, so here is our basic statement of completeness. If we've got a genuine entailment, then we can prove it. That's what we're going to try and establish. But in previous videos, we kind of played around with that a little bit to put it in a form that's actually going to be easier for us to prove. So here's what we came up with. If the tree that starts off with sentences X finishes open, then that set of sentences X is satisfiable, okay? So when you've got a finished open tree, the stuff at the top of it is satisfiable. How do we prove that? Well, think about what it takes for a tree to finish open. That basically means all the branches are finished, that is, we can't apply any more rules, and at least some of them are open. So what we're actually going to try to show directly is this. Finished open branches are satisfiable, okay? Because if we can show that, then we have in effect shown this, okay? If finished open branches are satisfiable and we've got a finished open tree, then it's got some finished open branches on it. And if they're satisfiable, then the sentences that we started with the tree are going to be satisfiable, right? So if we have some tree and it kind of goes a little bit like this, and maybe some of these branches close. But if we've got at least one branch that stays open, well, if this branch is satisfiable, and by that I mean all the sentences that we find along this branch, if together all of them are satisfiable, then it's got to be the case that these sentences here, the ones we wrote at the start of the tree, are satisfiable, okay? So if all of these are satisfiable, then these have got to be satisfiable. So if we can show that finished open branches are satisfiable, that's our way of showing that if an entire tree finishes open, then the sentences we started with are satisfiable. That's a special case of the general thing that we're showing. Okay, so we need to show that finished open branches are satisfiable. How are we going to do that? So we're basically trying to show an if-then. If this branch finishes open, then all the sentences on it are together satisfiable. That set of sentences is satisfiable. Okay, and to prove an if-then, we assume the if bit and we try to show the then bit. So we're going to say, let's assume that we've got this branch. Let's call it B, going down like this. Let's take it to be a finished open branch. And what we're going to try to do is show that all the sentences on that branch are satisfiable. And basically, if we've done that, then we're finished with the completeness proof. Okay, so how are we going to show that the sentences on this branch B are satisfiable? Well, to say that a set of sentences is satisfiable is to say that some model makes all of them true at the same time. So we're going to construct a model based on this branch and show that that model makes those sentences true. So we've basically got two jobs to do. Firstly, we've got to describe how we can take information on this branch and use that information to build a model. That's the first task. The second task is to establish that the model that we've just built makes all of the sentences on the branch true. So this kind of strategy is really, really common in completeness proofs, right? You basically always have to take some kind of thing that results from your proof. You have to construct a model and demonstrate that the model makes a certain bunch of sentences true. Now, we've already seen how to build a model based on a finished open branch. Okay, so if you're not too sure about that, go back a few videos and review how to do that. So basically what we're going to do is we look at all the names that appear along the branch. We're going to have things in the domain of the model that correspond to those names. They can be the names themselves, or they can be numbers or whatever. And then if we have a sentence FA, we're going to put A or whatever corresponds to A in the extension of F. And if we've got RAB, then we're going to put the ordered pair of the thing that corresponds to A and the thing that corresponds to B in the extension of the predicate R. Okay, so in that model, the A thing is going to be related to the B thing. So when we looked at that construction a few videos back, I just told you that if you do that construction, the model that you get out of it is going to make all of the sentences on that branch true. So not just these atomic sentences, but all the sentences, like complex sentences, quantified sentences, and so on. I just said that, but I didn't give you any proof. So what we're going to do now is prove that that model, the one we've just constructed, is going to make every sentence on the branch true. Right, at this point, I want to just pause the proof for a moment and try to clear up a mistake that a lot of people kind of fall into when they're going through this. Often when we're doing tree proofs and we're building models from finished open branches, what we're doing is we're working with a specific tree. Okay, so I give you specific premises and conclusions, and you draw the tree proof, and you've got a finished open branch, and you draw the specific model. Okay, that's a specific proof and a specific model. That's not what we're doing here. So we're talking about any set of sentences that we're going to bung in the top of the tree proof. We've got a finished open branch, and we're going to try and show that it's satisfiable. Okay, so we're not talking about a specific set of sentences in a specific model. We're talking about an arbitrary set of sentences and an arbitrary model that we have constructed from that finished open branch. Okay, so we're not actually building the model. I'm just demonstrating that the process that we go through to build that model is guaranteed to make all of the sentences on the branch true. So we need to prove that this model that we've constructed from the branch satisfies every sentence on the branch. So how do we show that it satisfies all the sentences? We can't go through one sentence at a time because we don't know what they are. This at the top is an arbitrary set of sentences, so we don't know what sentences we've got here. What we need to do is a proof by induction. So in logic, this is a really standard way of proving things. It's quite a complicated idea. I'm not going to go through why a proof by induction works in this video. I'm going to cover that in a separate video devoted just to explaining proofs by induction. So right now, I'm just going to do the proof. And if you're kind of puzzled about why it works, go and look at this other video on proofs by induction. So we're going to be considering sentences in terms of their complexity, okay? So it's a proof by induction on the complexity of sentences. Complexity can be measured in different ways, but just think of it as the number of connectives in a sentence. So the more connectives it's got, the more complex it is. For kind of technical reasons, we're not going to count single negations. So we just count something with a single negation as 0, but that's kind of a technicality. Don't worry too much about that. So we're going to begin with the case where a sentence has complexity 0, i.e. no connectives in it, so it's an atomic sentence. So something like this or this. And we want to show that if that sentence is on the branch, then the model makes it true. Okay, well that's pretty obvious because we built this model from the sentences like that we find on the branch, right? So if we've got FA on the branch, then we put the information that the A thing should be part of the extension of F into our model. And if we've got RAB on the branch, then we put the information that the A thing is related to the B thing. So the ordered pair of the A thing and the B thing is in the extension of predicate R in our model. So our model is guaranteed to make true sentences like this, all the sentences on the branch with complexity 0. What about sentences with just one negation in them? So things like not GB. Well, if we've got not GB on our branch, then because it's a finished open branch, we can guarantee that we don't have GB on the branch, right? If we did, we would have closed that branch because we applied all the rules, and then it wouldn't be an open branch. But we didn't do that, so we don't have GB on this branch. Okay, so the B thing, the thing that B picks out in our model, only gets in the extension of G if we've got GB on the branch. But we don't. Nowhere up here do we have GB. So in our model M, the thing that B picks out won't be in the extension of G. So our model isn't going to make GB true. It's going to make it false. And because GB is false in the model, not GB is going to be true in the model. So whether we've got 0 or 1 negations, our model will make true any sentence like that on the branch. Now we have to think about the more complex sentences, so the things with conjunctions, disjunctions, and so on in. We want to show that for any sentence like that, if it's on the branch, then our model makes it true. So what we're going to do is we're going to pick an arbitrary sentence A that's on the branch, and we're going to try and show that our model makes that sentence true. And to help us, we're going to make our inductive hypothesis. The hypothesis is going to be that for any sentence less complex than A, if that sentence is on the branch, then our model makes it true. So for any sentence that's less complex than A, if B is on the branch, then our model makes it true. We haven't proved that, we are assuming that. We can assume what we want, and that's what we're going to assume. We're assuming something about less complex sentences. We're going to try and show that this holds for the more complex sentence, A, okay? A can be any sentence here. So we're going to assume this and use it to show that if A, the more complex sentence, is on the branch, then it's going to be made true by that model. Now, exactly how we do this depends on what kind of sentence A is. Is it a conjunction, a disjunction, or whatever? We don't know, so we have to consider every case and show that whatever kind of sentence A is, that is going to follow from this assumption. We are going to keep coming back to this inductive hypothesis, so I'm just going to leave it there to refer back to. Okay, so we're going to go through case by case. Take our first case to be A is a conjunction. Okay, so suppose A is a conjunction, B and C. So what we're assuming here is we have this finished open branch, and on it we've got B and C. Now, because it's a finished open branch, that means we applied all the rules. So in particular, we must have applied a rule to this. And the rule for that would have added B and C to the branch. So one thing we now know is that B on its own is on our branch, and C on its own is on a branch. The other thing that we know is B is guaranteed to be less complex than B and C, right? Because whatever number of connectives B has got, it can't have as many as B and C. It hasn't got that one. Similarly, C is less complex than this sentence. So we can use our inductive hypothesis. Because the inductive hypothesis holds for all sentences less complex than A. In particular, it holds for that one and it holds for that one. And it says if they're on the branch, our model makes them true. So yeah, they're on the branch. So our model makes B true and our model makes C true. And we know from the truth condition for and that if a model makes one thing true and another thing true, it also makes their conjunction true. So our model makes true B and C. So what we've shown there is if our random arbitrary sentence is a conjunction and it's on the branch, then our model makes it true. So that was one case, okay? We are interested in this sentence, random sentence A on the branch, and we've shown that if it's a conjunction, then our model makes it true. We have to do the same thing for all the other cases. If it's a disjunction, if it's an if-then, if it's a negated conjunction, if it's a negated disjunction. So let me just show you one more case so you get the general idea. So that was a non-branching rule case, so I'm going to show you a branching case now. Let's consider what happens if A, the sentence we're interested in, is a disjunction. So now we're thinking about the case where A is a disjunction with the form B or C. Okay, so we reason the same as before. We're supposing that we've got this branch that's got B or C on it, and it's a finished open branch. So that means all the rules were applied. In particular, we applied a rule to this, and that would have meant that we branched left and right and put B on one branch and C on the other. Now, we might have closed one of those branches. Our assumption is that we've got some finished open branch that's got B or C on it. It might be this branch, it might be that one. We don't know which one, okay? So we have to consider two cases, the case where it's B, the case where it's C, but it's going to be the same either way around. So just like in the previous case, we can use the inductive hypothesis because B is going to be less complex than B or C, and also C is going to be less complex than B or C. And our inductive hypothesis applies for any sentence that's less complex than A, the one we're interested in. So we've basically assumed that any sentence less complex than this that's on the branch is made true by our model. So if that's the branch that stays open, then we can infer that M makes B true. On the other hand, if that's the branch that stays open, then it would follow that M makes C true. Now, we don't know which branch stays open, okay? We know that either M is going to make B true or M is going to make C true. I mean, it might be both, but we just can't say for sure. However, what we do know is that from the truth condition for disjunction, if M makes B true, then it makes B or C true. And in the other case, if M makes C true, then it makes B or C true. So either way, whether that branch stays open or that branch stays open, our model makes B or C true. Okay, so either way, B or C is going to be true in the model that we created from the open branch. So we've considered another case there, okay? The case in which A, the sentence we're interested in, if it's a disjunction, then yeah, our model makes that sentence true. Okay, so if you want to finish off this completeness proof, what you need to do is go through each and every remaining case. The if-then case, the if and only if case, the not and, the not or, and so on. Go through all of those cases showing that our model makes that kind of sentence true if that sentence is on the branch. Once you've been through all of the cases, then we can conclude that sentence A of arbitrary complexity is made true by our model. What we've shown there is that any sentence of any complexity, if it's on the branch, is made true by the model. So, all the sentences on the branch are made true by the model. In other words, the model that we constructed from the information on this branch satisfies all the sentences on it. That shows that finished open branches are satisfiable. And that's what we needed to prove completeness. And that completes our completeness proof. Okay guys, so if you're feeling confused there about exactly how we got from this kind of inductive hypothesis in a few cases to that result holds for all sentences, well, that's how a proof by induction works. It kind of seems a little bit magical, so if you're feeling confused about how that works, head on over to the video where I focus in on how proofs by induction work in logic. Hopefully that will help you out. Okay guys, thank you so much for watching this far. I hope you found this video useful. If you have, do me a favor, give it a thumbs up, and if you're enjoying this stuff, why not subscribe to the channel? So I'm going to be continuing this series. We're going to be doing more on proof by induction, we're going to be looking at decidability of the tree test. We're going to be looking at undecidability. So if that sounds good for you, I hope to see you back here soon.